Good morning, everybody. Welcome to day one of online learning for Prop and Stats. Kind of weird, huh? I hope everything is going well in your world. Everything's good in my world, other than I think I'm going a little insane being cooped up inside all day. But trying to get outside and get walks in and things like that. So I hope you are doing well. So yeah, we're just gonna hop right back in, I guess. This slide that you guys see in front of you is all the information we talked about before break. So we did have a quiz on this. I did get a chance to grade your quiz corrections from before our extended break and enter that in the grade book. But we are going to skip the Unit 6 test for now. But you still have to learn. There's one more piece of information we were going to learn the week before break that we didn't get a chance to get to. So just a couple of reminders. We were talking about sampling distributions. So a typical sampling distribution follows this rule. And if it's binomial, you can use the binom PDF and CDF. But most of the time it was a normal distribution where you could use normal CDF, which was good. The main thing that allowed us to say that was this if the large counts condition was met. So if you plugged in n and p into both of these equations and they were both greater than or equal to 10, that meant you could use normal CDF and it wasn't a problem. So the last thing we talked about was the equations when we're doing a sampling distribution for p hat or a sample proportion. So remember, the whole idea is we're taking multiple sample proportions and plotting them on a graph and looking at the graph overall to make an estimate as to what is the actual true mean of this proportion, basically. So today where we're going to pick off is we did sampling distributions in general. We talked about proportions. So it only makes sense for us to start talking about a sampling distribution of a sample mean. So remember when Mr. Ramirez's class did the penny for your thoughts activity at the beginning of the chapter? We did that in class as well, where you got pennies, sample size of 5, and you had to find the average mean, basically, for those 5 pennies, and then we plot them on a graph, okay? Well, so the formulas we can use for this, just like for sample proportions, for sample means, are these two formulas right here. So the mean of a sample mean, basically, is just the mean of the data set in general, and the standard deviation is the standard deviation of the data set in general divided by the square root of n. We'll do some examples so that you know where these numbers come from. Remember, the formula for the standard deviation of the distribution of x bar requires that the observations be independent. So if you remember bins, I was that each trial is independent of each other. So remember, we said we can kind of fudge the independence rule if the sample size is less than 10% of the population size. So if we're talking about a sample of 5 pennies and our population was, 1,000 pennies, well, obviously we're okay to kind of say technically they were dependent probabilities, but we can make it work. So let's do a practice problem. The number of movies viewed in the last year by students at a large high school has a mean of 19.3 movies with a standard deviation of 15.8. Suppose we take a simple random sample of 100 students from this school and calculate the mean number of movies viewed by the members of the sample. Calculate the mean and standard deviation of the sampling distribution of x bar. At this point in time, pause the video, give this question a try, and then unpause it to get the answer. So when you are ready for the answer, our equation was the mean of x bar was just the mean. So in this case, the mean was 19.3. So that's pretty easy. We didn't even have to do any calculations. We just pull it out from the equation. And then the standard deviation equation for a sampling distribution for x bar is the standard deviation of the entire sample divided by the square root of n. So the standard deviation was 15.8. And n in this case, we're taking a simple random sample of 100 students. So I'm going to type that into my calculator. Square root of 100 is 10, so 15.8 divided by 10, I get 1.58. So I just did that off to the side. I know you can't see that, but I just used my calculator to help us out with that, okay? So nice and easy. The formulas are just as easy to use as sample proportion was, thankfully. So here's the other thing that we need to talk about is when we're talking about sample means, they work a little bit different than proportions. Remember how we had to do the weird like NP is greater than or equal to 10 and all that to make sure that we can use normal CDF? Thankfully, because of the central limit theorem, we can actually make that a lot easier. The sampling distribution of the sample mean is approximately normal when n is large. Now, here's the problem with that. What does large mean? Some people think 10 is large. Some people think, well, large would be like 1,000. So what's the rule? So statisticians came up with a more formalized rule that says if the sample size for a sampling distribution of a sample mean is greater than or equal to 30, even if it doesn't 100% look like it's a normal curve or anything like that, we can still use normal CDF. It is allowed. So let's do an example problem so I can show you what I mean. Here, for example, here are dot plots showing the simulated sampling distributions of the sample mean for 500 simple random samples of size 2 in this case, and 500 simple random samples of size 50 in this case. Notice how this one is a little bit less skewed versus this one is much more normal. And that's kind of the idea. Okay, so thanks to that central limit theorem, as long as n is greater than or equal to 30, we can say it's roughly normal and it's okay to move forward. So for example, in this question, describe the shape of the sampling distribution of x bar for simple random samples of size n equals 2. Well, my assumption is if the population is left skewed, that is not a very big sample size, so I would assume this one would also be left skewed. Notice how n is not greater than or equal to 30, so I don't think we can use normal CDF. But if we were to take that same sample and use a sample size of n equals 50, now we can say approximately normal, and it's allowed. Okay, so just practice using that central limit theorem. So let's tie this all together to try to clarify this a little bit. Suppose that the number of texts sent during a typical day by the population of students at a large high school follows a right-skewed distribution with a mean of 45 and a standard deviation of 35. How likely is it that a random sample of 100 students will average at least 50 texts per day? So I know we're talking about mean, right? A sampling distribution of sample mean. So I start with my formula. And the mean is, in this case, was 45, so the mean of the sampling distribution is also 45. The standard deviation of the sampling distribution is the standard deviation divided by the square root of the sample, and the sample size is 100. So 35 divided by square root of 100, I get 3.5 for the standard deviation of the sample mean. Okay, so then the whole question is asking, will average at least 50 texts. Well, to be able to do that, I need to know if this is normal or not. Because this sample, right, this is the only thing I have to check, which is really nice. For proportion and for regular sampling distributions, we had to do that n times 1 minus p, which was a little more complicated, right? This one, it's purely if it's greater than 30, sweet. In this case, our sample of 100 is greater than or equal to 30, so we can say that it's approximately normal, allowing us to use normal CDF. Our lower bound is 50. Our upper bound needs to be a really big number, so let's say like 1,000. If you're using a 89 or a nicer TI, it might ask for infinity, comma, the mean is 45, comma, the standard deviation is 3.5. I'm going to type this in my calculator off to the side. I did post a link to a free TI graphing calculator emulator that Texas Instruments is allowing students to download for the rest of the school year, which is really super nice. So check that out on Google Classroom if you haven't already. It's really easy to download. It doesn't take up a lot of room on your computer, I promise. But that's something you're going to want to be able to do these calculations moving forward. Okay. All right. So here is another practice problem for you. What I would recommend is pausing the video at this point in time, and then when you are ready, go ahead and unpause it, and I'll show you the answers. All right, so what is the shape of the sampling distribution of x bar for samples of size equals n equals 70? Justify. I would say, I know I can't do a very good full sentences on here, so I'm going to do the best I can with kind of like note taking and bullet points. But it's definitely going to be approximately normal. because the sample size is 70 and 70 is greater than or equal to 30. Therefore, the central limit theorem says it's approximately normal. Okay, so it's going to allow us to use like normal CDF, that sort of thing. Sorry for my handwriting, by the way. This stylus I'm using isn't perfect. I have a new one coming on the way from Amazon, so we'll see if next week's videos are a little better. All right, calculate the probability that the average maintenance time X bar for 70 units exceeds 1.1 hours. So exceeds 1.1. So I'm thinking normal CDF, 1.1 comma, and then let's do like 1,000. And we got to find the mean and the standard deviation. Well, the mean, remember, is just the mean of the population, which they gave us as 1. And then the standard deviation is whatever their standard deviation is divided by the square root of the sample. Well, the sample is 70, and the standard deviation was 1.5. So square root of 70, I type that in first, and then I do 1.5 divided by that answer. And I got 0.179. So I'm going to type that into my graphing calculator, hit second distribution, normal CDF, just like we did before break. Remember, use that free TI calculator download if you do not have a graphing calculator at home. Okay. All right, based on your answer to the previous problem, did the company budget enough time? So this is basically the probability that the time exceeds this 1.1 hours is 2.8%. That's a pretty small probability. And so when they're asking, will this be enough time? Okay, the likelihood of needing more than 1.1 hours is only 2.8%. We briefly talked about how 5% is kind of the cutoff in statistics across the board. It is typically in other disciplines like biology and things like that as well. So since it's less than 5%, 1.1 hours should be just fine. All right, so here's that same summary page from the beginning. This is all the new stuff from today, okay? I am going to assign a homework assignment just like we normally would. My goal with all this online learning is to try to keep our class as close to what you guys are used to as possible so that you have something familiar to latch onto during these like really weird times. So take a look at the homework assignment. The answer key will be posted as well to kind of help you through, but use these formulas and get some practice. If you have questions about this lesson, feel free to come talk to me during office hours. My office hours are posted on Google Classroom underneath the important information like syllabus tab up at the top. So you can see where the link is to come see me. And it's like a Skype meeting basically. So there will be other students possibly there that also need my help. Just, feel free to stop by, say hi, ask a question if you have it, and I'll make sure I'm available for you guys. Okay, good luck with this. You got this. Please let me know if I can help or if there's anything I can do to make things more clear. Nice work.